Hi there, this is Professor Shannon Gracie from Miracosta College. We are back with section 10.4 from Blitzer's Introductory and Intermediate Algebra for College Students text. And today we'll be learning how to add and subtract radical expressions, which is just like adding and subtracting variable expressions, also known as like terms and that kind of stuff. We'll be using the quotient rule to simplify radical expressions and to divide radical expressions. So why don't you guys go ahead and do these warm-ups, A and B. So pause the movie and do the warm-up. On your mark, get set, go. Alrighty, let's see how you did. So for this first one, we have 8 divided by 2 is 4. We have x to the 3 minus a negative 2 and y to the 5 minus 2 using properties of exponents, which gives us a result of 4 x to the 5th y cubed. How'd you do on that one? Awesome. I knew you could do it. Okay, for the next one, we have 3xy squared times the cube root of 16x squared y squared. So remember, when you have a cube root, you're looking for perfect cubes. So we can go ahead and we've got the 3xy squared that we leave alone times the cube root of, I know that 8 is a perfect cube, so if I write it as 8 times 2x squared y squared, I'll be able to take out a 2. So this will be 3xy squared times 2 from that cube root of 8. And then we still have the cube root of 2x squared y squared left. And our final result is 6xy squared times the cube root of 2x squared y squared. How'd we do on that guy? Great, great. Okay, now next up, my apologies. If you need to pause the movie to go get a separate piece of paper, I forgot to put my little spiel about adding and subtracting radical expressions. So I'm going to go ahead and I'm going to add in a page. I guess we'll go ahead and we'll do it below, and then we'll go back to the quotient rule for radicals. So here we go. So we're going to, whoops, file, edit, page. I'll append page so it goes behind. And so what we'll have is we'll have a new section. So this section is adding and subtracting radical expressions. Oops. All right. So you want to think about, what does it mean to have like terms? If you recall, like terms, when you're talking about polynomials, have exactly, or they could be rational expressions, but they have exactly the same variable factors and can be combined. So if we think about it, let's suppose we had 17y plus 14y. This one, you can literally, if you wanted to, you can factor out the y, and you're left with 17 plus 14, which gives you y times, what is that, 31? which is equal to 31 y's. Okay, so we looked at the variable. They each had a variable of y to the 1 power, and so therefore we were able to combine the coefficients. And this is just, you haven't been doing this for a while, but this is why it works. Now if you consider, what if we had 17 times the square root of 5 plus 14 times the square root of 5? Well, you could literally factor out a square root of 5, because remember this is 17 times root 5 plus 14 times root 5, and you'd be left with 17 plus 14, so you would get root 5 times 31, which is 31 times root 5 is how we usually write it. So it's the same concept that we've used for combining like terms. So remember, this had the same variable raised to the same power. This has the same base raised to the same power. So here, if you look at these and you think about it in that way, this is 17 times 5 to the 1/2 power plus 14 times 5 to the 1/2 power. So these guys here, you've got the same base raised to the same power. So how does that work for radicals? Well, for radicals, this means that you would have the same radicand and you would have the same index on the root. So that's what we check for when we're dealing with radicals. So let's write that in. Two or more radical expressions that have the same indices and the same radicands. So the same index on the radical and the same expression inside the radical. These are called like radicals. Like radicals are combined exactly the same way that we combine like terms. The tricky part is sometimes you have to simplify the radical before you see that they're like radicals. So that's where there's an extra layer of work. Okay, so let's try this one. Let's say we had -3 times the 4th root of x minus 15 times the 4th root of x plus 12 times the cube root of x. This will be, so here we go. Let's look at the radicands. Each of the radicands is good. The radicands all are x. Okay, but let's look at the indices. So for the first term, the index is 4, the radicand is x. The second term, the index is 4, the radicand is x. So these are like radicals. But the third one, the index is 3, and the radicand is x. So since the index is different, this is not alike with the others. So we leave it alone. So we can combine the two I underlined in red. So -3 minus 15 is -3 Good, 18. And then we have times the fourth root of x, and then plus 12 times the cube root of x, and we're all done. Okay? All right, so now we can go ahead. We'll have a little more practice later on in combining like radicals. So now what we can do is we can go back up here to the quotient rule for radicals. So if the nth root of a and the nth root of b are real numbers and b is not equal to 0, then it turns out the nth root of the quotient a over b can be split into the quotient of these two nth roots. So, in words, the nth root of a quotient is the quotient of the nth roots of the numerator and denominator. So, coming down to the example, here, when I look at this problem, the square root of 20/9, what I see is that there's a perfect square within 20 and 9 is a perfect square. So if I split these radicals, I would get the square root of 20 over the square root of 9. Well, the square root of 20, we can write that as the square root of 4 times 5. I did that because 4 is a perfect square. And the square root of 9 we can evaluate as 3. So now we'll have the square root of 4 is 2 times the square root of 5. You know what? I'm going to come up here. So we'll have the square root of 4 is 2. And then we'll have times root 5, because we can't do anything with that, over 3, and we're all done. That is simplified. Okay, now, similarly, we're looking for cube roots. So this is equivalent to the cube root of x to the 6 over the cube root of 27y to the 12th. This is equivalent to the cube root of x squared cubed. Remember, I want perfect cubes. So when you raise a power to a power, you multiply. And then down here, this is times the cube root of 3 cubed, which is 27, times y to the 4th cubed, because y to the 4th raised to the 3rd power gives us y to the 12th. Now we will have x squared, because that's what was being cubed in that top radical, and then the denominator will get 3y to the 4th. And we're all set. How's it going? Going okay? Awesome. All right, so next up, dividing radical expressions. Sometimes you can simplify better by dividing the radicands, all right? So it just depends on the situation. So here we go. If the nth root of a and the nth root of b are real numbers and b is not equal to 0, because we don't want a 0 denominator, then the nth root of a divided by the nth root of b is equal to the nth root of a over b. So to divide two radical expressions with the same index, they have to have the same index. Divide the radicands and retain the common index. Okay, so example 2. the numerator is a square root, the denominator is a square root. I see that I can combine things within the radicands. So if I make 1 happy square root, it's going to be easier to simplify this problem. So 3 goes into 120 40 times. So this will give me 40x cubed when I simplify, which I can now break into, what perfect squares I have. So this will be the square root of 4 times 10, because 4 is a perfect square, times x squared times x. So I'll be able to take out a 2, because 2 squared is 4, and an x, and then I'll have 10x under the square root remaining as a multiplier. Okay, why don't you go ahead and pause the movie and try part B. Okay, let's see how you did. This is equivalent to, again, it's going to be, I have, like factors here, so I'm going to write it as 1 happy cube root So 128 divided by 2 is 64. So I'll get the cube root of 64. X to the 4 minus 1 is x cubed. Y to the 2 minus the negative 4 is y to the 6. So then I'll have the cube root of 4 cubed is 64. I have an x cubed. And then I have y squared to the 3rd to the cube. So my end result will be 4xy squared, because those were the quantities being cubed. All right, so example 3 kind of puts everything together. So why don't you go ahead and pause the movie and see how you do on these, all right? Good luck. Okay, let's see how you did. Just kind of a reminder, this is just like 1 root 2 plus 5 root 2's. So the radicand is 2 on each of these, and the index is 2 because it's a square root. So we can combine them. This will be 1 plus 5 is 6 times the square root of 2. And I'm done. That one was a short one. Now part B, this is what I was talking about before. Part B, we need to simplify the radicals and then see if we have like radicals. So here we go. This will be negative. We have square root 20. So that's square root 4 times 5. And then we have an x squared times an x. That's the same as x cubed. So this will be, and then plus 3x times the square root. Now 16 is a perfect square. So 16 times 5 is 80 times x. So now what we'll have is negative. We can take out a 2 and an x, so we'll have negative 2x. And what we have left is the square root of 5x. And then over here we can take out a 4, so we'll have 3 times x times 4 times the square root of 5x, which is negative 2x root 5x plus 12x root 5x. So now do you see we have like radicals? The radicands are each 5x, and the indices, the index on each of them is 2. So we can combine these to get negative 2x plus 12x is positive 10x times the square root of 5x. And we're done. Okay, part C. This is going to be root 27 is going to be root 9 times 3 over 2, because 9 is a perfect square. Root 75 I can write as root 25 times 3, because 25 is a perfect square, and that's over 7. This will give me root 3 over 2 plus 5 root 3 over 7. I now need to get a common denominator. So if I multiply this one by 7 over 7 and this one by 2 over 2, I'll get a result of, so I'll do 3 times 7 times root 3 to get, let's see, we'll end up with 21 root 3. 5 times 2 is 10 times root 3, so plus 10 root 3 all over 14. So that's making one happy fraction now that I got a common denominator of 14. And then 21 plus 10, now I have like radicals up in the numerator. So 21 plus 10 is 31 times root 3 all over 14, and I'm done. All right, in our last problem, we'll have, first of all, I want you to recognize that we can simplify the 16x to the 4th and the 8x cubed. So that's going to give us 2x to the 1 times, I'm going to make this one happy cube root. And then similarly, 20 divided by 4 is 5. Make one happy cube root. And we'll have 2x times the cube root of 3 goes into 48 16 times. X to the 3 minus 2 is x to the 1. Y to the 2 minus 1 is y to the 1. Minus 5 times the cube root of 2, x to the 3 minus a negative 1 is x to the 4th times y. So now we will have 2x times the cube root of 8 times 2 times x times y minus 5 times the cube root of 2 x cubed times x times y. So we're almost there. So now we'll have 2x times the cube root of 8 is 2, and then I'll have the cube root of 2xy remaining. And then I can take out an x, so I'll have minus 5x cube root of 2xy. Sorry, that looks running out of space here. So then we will have 4x times the cube root of 2xy minus 5x times the cube root of 2xy. So now we have the same index of 3. Put this closer. Same index of 3, and then with same radicand of 2 times x times y. So we can combine the 4x and the negative 5x to get negative x times the cube root of 2xy. All right, so that is it for 10.4. Don't forget to do some problems from the 10.4 problem set, and have a fabulous day.